I can't resist pointing out that in your discussion of the Ella Schmidt-Clark Fandango, that they and the relationship to Groch's own claims, they violated what I call Groch's first law of argumentation, which is what Clark did, just never prove something that's false. Yeah. And Groch himself violated his own first heuristic principle of argumentation, which is counterexamples are easier than proofs. So I think everyone was in the wrong.
Everyone was,
at least with regard to Bob G's own, principles for argumentation. But more seriously, I was thinking when you were talking about the conformal factor in the Mr. space-time. Yeah, I was going to point out that almost certainly, but then you beat me to it. That almost certainly you're going from vacuum to non-vacuum, and so it's not just that you lose the energy conditions, but I think you can make the case even stronger. That basically what's happening is something like the field equations for matter are changing, where the conformal factor becomes non-trivial. So I'm just curious. So I have a series of questions. One is, do you think that a condition like that you might be able to formalize in some way and use as an investigation? Second question is about the nice duality that you pointed out, loosely speaking, duality between J-hole freeness and chronology. It kind of very, very crudely, loosely reminds me of the similar duality in black hole and singularity spacetimes between chronology and the existence of singularities. You can often trade off between the two. And I'm wondering if you thought at all about investigating a similar line of thought, whether you can trade off J-hole freeness for singularity, since you can do it with chronology. And if so, that might actually be a nice way for you to show that being non-J-hole free is generic in some sense, since we think that in some crude sense having singularities is also generic.
Yeah. The idea of holes and some causal condition doing this trade-off, I think pops up in a lot of places. I was thinking about like the cosmic censorship hypothesis, where you're considering some initial slice and then evolving it, and of course, if you're willing to consider strange models of the universe like Misner or Taubnut or others, you're going to violate cosmic censorship. You're going to have some kind of naked singularity, some kind of hole there. But if you put restrictions on the kinds of causal structure that are allowed or not allowed, like in the standard one in Wald's book, strong causality is used there, then it may be that you can show that every such evolution is maximal, so there won't be any holes there. So yes, I realize that there is this duality, and it does pop up place to place. Remind me of your first question again. I remember it had to do with the
fact that the explicit construction of your example relied on this conformal factor that essentially makes vacuum turn into non-vacuum just kind of spontaneously. Yeah. So one way to think about that is that kind of spontaneously, for no reason at all, the kinds of matter fields you have there just change.
So maybe an energy condition or something could rule that out.
I'm wondering if there might be a way to try and make that idea rigorous and precise and prove similar results about it.
I see. Well, I mean, honestly, I haven't been able to figure out yet if the example that I gave satisfies the energy, like the standard, like weak energy condition, for example. I doubt it does, but maybe. But that would certainly be a precise question, and one could look at it. And also, you could make an energy condition like that. You could sort of limit your discussion to not just vacuum spacetimes, so nice spacetimes that are vacuum, but nice spacetimes that satisfy some condition like that. But yeah, I'm thinking along those lines. I need you to help me.
I'm not a young whippersnapper, sorry.
Yeah. Okay. Sorry.
This may be a dumb question, but what actually happens if an event is going along through space-time and hits a hole? I have a much, like when you intuitively say time machine, even though it may or may not be some device, it would still be something where you get strange behavior with the direction of time. But what happens if my event hits a hole?
Yeah, I think it definitely matters what definition of hole you're using. J hole freeness actually turns out to be quite interesting because you can have geodesically complete J holes. So you might think, okay, well if you've got a J hole, then you're going to pop into that hole and then you're going to go away. But if I made my conformal factor go to infinity instead of 0 there, then actually the proper time of that journey to go into the hole, I mean you do go into the hole, but it takes you an infinite amount of time to go in there, so you don't really pop out of existence in the same kind of way, right? On other hole freeness conditions, some that are more standardly used, one that's called local inextendability or a version of local inextendability, then that would be a case where you're gonna pop out of existence, and maybe you'll pop back in or something, but there's no guarantee.
Yeah, I'd like to know more about how you're thinking about physically admissible spacetimes. So you suggested the following things, that you think that we can't know which spacetimes are physically admissible, right? And so it sounds like you're thinking that there's some unknowable fact about which spacetimes are physically admissible. Like I'm kind of like, like what. What kind of framework is behind? Are you thinking that there's sort of like laws kind of in addition to the bare field equations, like some set of energy conditions, for example, that are the right ones, but it's kind of impossible to know which ones or something? Is that kind of the idea?
I'm just thinking of some questions posed by Clark Leemore and David Malaman back in the 70s concerning observationally indistinguishable spacetimes, and just the idea that given any spacetime or almost any spacetime, you have an observationally indistinguishable counterpart that has wildly different properties.
Oh yeah.
So,
sorry. The part that I feel like I would like to understand better is not we can't know what the rules are, which I sort of like. I feel like I understand your reasons for that. What I find less easy to kind of get a grasp on is what sort of thing you think is determining the facts about what the rules are, like determining the facts about which spacetimes are physically reasonable or not. Because it's not which spacetimes we kind of should guess we live in, right? Because we don't know anything about that. So what it, yeah.
I guess I'm having a hard time understanding the question. So can you
well,
give me a
okay,
possible answer, and I'll tell you if I agree.
Well, so one possible answer would be that there's just some kind of basic fact about what the laws of general relativity really allow or really don't allow, and it's just, that's something we can't determine the answer to, but there's just a fact about it, right? I mean, that's the only thing that kind of pops into my head, but as a kind of possible way to answer that question, but I guess it doesn't strike me as something that I would expect you to say necessarily. So I'm kind of wondering.
I guess I just think that P, the dot, so consider the space of spacetimes, that the physically reasonable ones are a subset, right? And so I don't think it's the whole space. I think some there are
subset of the models of GR.
Some subset of the models of GR don't belong in that P. Now I'm claiming that we can never know what the P looks like, but that doesn't mean that I don't believe in a definite P. I also am weary of trying to say too much. I don't want to say anything I can't, defend here, and I don't want to claim that some of these crazy models, like ones that allow for time travel, or ones that allow for holes, are excluded, because we've seen, like in the history of GR, that, like, for example, people thought singularities themselves were just artifacts of the theory until, you know, the singularity theorems. And so I really, you know, Howard's paper that I started with at the beginning was a paper where he looked very carefully at Gödel's space-time and Gödel's arguments for taking seriously the possibility of some of these strange models. And God, I'm so glad I'm in that line, like from Howard to David to me, because that's so interesting to me. To take seriously that crazy stuff. It's just, I can't tell you how happy it makes me.
No, me too. I guess part of, maybe if this is a rhetorical question, which I don't know if it is, I feel like if I thought that P was smaller than the whole bunch of spacetimes, it would be because I thought I had some reason to think these are the rules that say what's in P.
Yeah, and I'm going to say, how do you know what the rules are?
Right. So then, how do you know that P is smaller than all the spacetimes? That's kind of a.
I don't.
Yeah.
And that's why, for an example,
Yeah.
for this one, it's wonderful that there's nothing to constrain.
Yeah.
This could be the entire class.
Okay.
And the existence result
Okay.
will go through. And that's why I think, in the case where P turns out to be really large, that's why that's why Hal has this, you know,
Yeah.
trump card
Yeah.
that he can play because of stuff
Yeah.
like this.
Okay.
The line by the way goes back to Gödel, yes?
Gödel, yes, it goes back to Gödel.
Yeah, so this is kind of out of left field, but one thing that I found interesting years ago when I was looking at this stuff is that there were proposals by people like Bernard Kay to say that you had to restrict the space of possible spacetimes in order to be able to formulate a quantum field theory. So he had this condition called F locality, which was a further condition that I don't actually remember the details now, but it was, you know, the idea was that in order to have a reasonable matter theory, there might be some things that classical GR allowed that you couldn't actually formulate a quantum field theory and curved spacetimes approach on that, you know, weird spacetime. And so that would be one way of
That would be, that's a good
changing
suggestion.
the rules a bit.
Yeah.
And have you looked at any work on this, or is this something that, I mean, I guess they'd probably all be local properties, so.
So is it the case that you could take one of those properties, translate it into classical GR as a precise
Or even
thing?
to say, we're not just interested in classical GR, we're interested in GR as its an approximation of some further theory, and so we might have some insights into a restricted space of possibilities based on that further theory.
Yeah, I haven't done any work there, but
Okay.
I need your help for that one.
Can I ask a question?
Yeah.
Not exactly a view, but of Bob Wall. So if we have some spherically symmetric matter distribution and it collapses into a black hole and then that black hole evaporates, would you expect that whole space-time to be J-hole free?
No, I mean, if you look at, so I'm imagining that there's a sort of evaporation point that isn't now in the space-time. So if if that point, if you go up to the future and that point were in your past, then the event horizon of the black hole wouldn't make it into your past. Well,
Yeah. So
basically never would, but arbitrarily. But would you be able to get arbitrarily close on? Yeah. Well, I mean, the issue is whether the past is closed. So the past would include everything outside the black hole in this example, but it wouldn't include the event horizon, which is in the closure of that.
So I'm inclined to say that the J-hole machine person is in a very good position because a collapsing star could be a starter.
Yeah, sure. Yeah. And I was going to say that the Schwarzschild solution is globally hyperbolic, and so it is J-hole free too.
It is J-hole free. Yeah, that's right. But after
But
it's not.
after it,
Evaporation is not. Globally hyperbolic. Yeah. So if you take if you agree with Kareem, and think that we have evidence for Hawking radiation, and so
Yeah.
on, maybe you should be a real fan.
yeah.
Of the whole machine.
I'm not invested either way, so I don't really care. I don't care which way it goes. I just think it's interesting that there are so many open questions that can be. It's a very simple. I mean, hopefully you all understood everything, and and these questions are so simple, and there are so many of them, and we don't know so much. Some of them are very hard, but as you can see, some of them are easy. It just takes thinking about things a little bit. So,
On a follow-up from that, I mean, if J-holes are totally okay, is there no hope for time machines? Like, if we consider the physically admissible spacetimes to include.
Not necessarily. I mean, if you consider another whole freeness condition instead, and
Right.
all physically reasonable spacetimes are whole free in that sense, and you can show a p time machine existence result for p for that condition, then
Is it likely to be one that's not satisfied by an evaporating black hole, though? I mean, who knows? But I trust your guess better than mine.
yeah, you'd have to look because I think it really depends on the formulation of the conditions. So.
Okay, please join me in thanking JD.
Since we are in fact 13 minutes ahead of schedule,